Alrighty, welcome back everyone. So for this question, we have a really cool and exciting way to think about things and to organize our thoughts of what we have and what we need in a nice convenient table. This will test our understanding of systems, when to use a formula, when to not use a formula, and how things move under the Lorentz transformation. So let's dive in. To start, we have two charges plus q minus q, and they are on parallel trajectories a distance d apart, moving at equal speeds but in opposite directions. What we're interested in is the force on positive q due to negative q at the instant they cross. Fill in the following table, doing all the consistency checks you could think of along the way. All right, so in system A, what we'll show on the next page is what we want to know is the E at Q due to negative Q, the B field, and the force. Okay, so we're going to want the electric and magnetic fields, and of course the force there when we're moving in a classic kind of system, opposites. Okay, system B, we want to hold plus Q at rest, and then system C, we want to hold negative Q at rest. So we get three different systems here. Let's dive in and see how everything comes together in a nice formatted table. All right, so what we were told to begin with is that we had a plus Q and negative Q separated by distance D. Okay, we see that. They're traveling parallel to the x-axis, Z pointing up, and Y is perpendicular to both. What we're interested in is the force on positive Q due to negative Q at the instant they cross here. So it looks like as when they hit the y-axis, again, we're going to the right for positive Q, we're going to the left for negative Q. They told us equal magnitude, opposite direction. Now let's dive in and see how relativity and the relativistic regime can make these things change. All right, first and foremost, what we have to understand is that for system A, theta equals 90 degrees. So the separation vector big R is equal to dy hat and theta hat is equal to z hat. Okay, so when we plug it into the electric field formula for charges moving, you see we get our constant 1 over 4 pi epsilon naught with the negative q times the v, all this stuff, and the sine squared here. We saw some of this back in chapter 10, I believe. But nonetheless, let's go ahead and shove it down where this is r hat over r, so over r squared. So we use vector identities to put that as r vector, or yeah, r vector hat, excuse me, r vector over r cubed. Nonetheless, let's keep pushing through. We see that it reduces down here to y hat over d squared, so everything is still the same. But you see that with sine of theta equal 90 degrees, since they're moving parallel to one another, they form a 90-degree angle when we're looking at D. So pretty cool there. We see from that a factor from the 3/2 here, which goes to 1/2 plus 2 over 2. That 2 over 2 cancels with this thing in the numerator. So what we actually boil down to is 1 minus v squared over c squared to the 1/2 power, which is gamma. So that's wonderful. This simplifies really, really nice. And so we see that the electric field is negative Q, again, because it's negative Q onto positive Q, or at positive Q from negative Q. So we're cool there. They're 90 degrees separated. And now we see that we're exactly what we thought we were going to have to be. Similarly, with this setup, the B field comes from a similar equation, and we just have to plug the 90 degrees in, and we see that 90 degrees sine goes to 1, 1 squared is 1, and we'll get the same kind of force factoring, or not really force factoring, but the 2 over 2 from the 3/2 power cancels with what's in the numerator. Cool, we like that. What we're doing now is we're trying to force our way into making the units the same for comparison's sake. So what we do is we multiply this B field term in the first line by c squared over c squared. We know we can multiply anything by 1 and get the thing back. And we do that because we know that c squared is equal to epsilon naught over mu naught, so we can cancel the mu naughts and write everything in terms of c squared and epsilon naughts. So with that, that simplifies nicely. We're cool with that, easy enough. We get negative q over 4 pi epsilon naught v over c squared gamma d squared z hat. Pretty cool, pretty easy. We kind of expect the b to have the v over c squared anyways, back from a couple of the special cases we saw with how the fields transform. So now onto the force. We want the force on positive q from negative q. So we have E plus negative, the negative because we're traveling in opposite directions, x hat plus or x hat times v or b, where it's the cross product. So we just plug everything in and we see that we get z or x cross z after the substitution of the fields, which yield a negative y hat because we could switch the order, get y hat, but we have to do it at the cost of a negative. The two negatives cancel and we could factor out a y hat. So our force here is kind of what we expected, where we have gamma and then this 1 plus v squared over c squared and the y hat. So everything's looking pretty good for system A. Okay, let's spice it up though. For system B, the speed of negative q is vb, and we have to use the Einstein velocity rule again here. So we get 2v up in the numerator, and we get that we have 1 plus v squared over c squared. Remember, we're holding positive q at 0 at rest, so the frame has to move opposite of that, and that moves in the direction of vb, so we like that. Cool enough. So our Lorentz contraction for system B, or Lorentz contraction, the Lorentz factor for B, system B is as such. VB, we have to substitute in from the velocity Einstein rule, or Einstein velocity addition rule, excuse me. So doing that and squaring it, we end up with this gigantic mess in the numerator or denominator. So we have to be careful how we wish to approach this. It's easiest to try to factor out that denominator squared term. So we do a force factor and we put the force in on a 1. So this was a 1 before, and we just put the factor of the denominator in there. And then we're still left with minus the numerator, which is 4v squared, and then the c squared stays there. The reason why we do this is because the 1 over 1 plus v squared divided by c squared squared, that's a squared term, and we could take it outside the radical, which is what we do in the next step. After that, what we do is cancel. Well, what we do is we FOIL out the squared parentheses that we put in there in order to factor. And once we distribute, then we can cancel factor of the 2 with the 4. Again, note that we're dividing by a fraction, so we multiply by the reciprocal. So in the next step, that's why we have the 1 plus v squared over c squared in the numerator. And we see that we get to a negative 2 instead of a positive 2 because we factored that positive 2 or canceled that positive 2 with the factor of the negative 4. So what we see here is that we have a 1 plus a cross term plus a square, so we can factor that down. And we see that we get the square root of a square. Voila, they cancel. We like that. And so what we see here is that we end up with a 1 plus the v squared over c squared and then 1 minus the v squared over c squared. And this is actually easy to deal with because what we can tell you is that this thing down here in the denominator is equal to the normal Lorentz factor squared. So the Lorentz factor for system B is gamma squared times 1 plus v squared over c squared. That is incredibly cool and compact. So all we have to do now is take the field that we had before and transform it. So here we know that for a stationary or quote rest charge, the transformed field will look like gamma b times the field of a stationary charge, which that's just gamma b times the field of the stationary charge, which is negative q over d squared. Again, the separation distance squared. This point's again in the y hat. Fantastic, easy enough to deal with. We like that. As you see, changing the gamma or the Lorentz factor for the particular frame shift is probably the messiest part about this, but then the fields transform as you would expect. The other field transformation that we need to do is the B. So the B of the moving field is 1 minus c, or of the moving stuff is 1 minus, or 1 over c squared, the velocity in B cross the transformed E field. So again, we saw from the Einstein velocity rule what VB is. So we just take that and cross it with the transformed field. Again, we get a z hat because if we're traveling in the x direction and we cross it with the y direction, x cross y gives a z. That's where we're at, and we see we get a nice cancellation. We love good cancellations. And then we can reduce this down to negative 2v over c squared, the normal constants we see, gamma squared over d squared, again in the z direction. So if we want the transformed force, we just have q, positive of course, times E, okay? And what we show here is that that is just equal to gamma F. Again, if one of them is moving, so positive Q was held constant or static, then that's not moving. So the only force here from the other one comes from the electric field that it has. So Q1 and Q2, and that's where we get the Q squared. So everything is working out good, and we just have to be careful of how we define the fields or how we define the frames because they affect which field formulas we use. And so our last system to encounter here is system C. So the speed of plus Q, now that that's moving and we're holding the other one stationary, we see here that we have negative V plus V because we're moving the frame in the opposite direction of this original Q direction that we had in order to account for it. So we get negative V plus V over all this denominator, so that's equal to 0. Lovely. So we see that gamma C is equal to 1. That makes our life incredibly easy. So E bar is equal to gamma C over E, gamma C times E, and we see that that's just 1, so we push on through. We like that. We get a similar result. B bar, we get a similar result because it goes to 0, because VC is 0. Perfect. We like that. Again, 1 for the force, 1 charge is considered stationary, so we only have to use QE since the B field is 0. And then we end up with gamma F again. Wonderful. We can deal with that all day long. But again, be careful with how we wish to dispose of this because if negative Q is at rest, we see that we get a negative sign there, so just be careful. But yeah, here's our summary table. And in A, the figure that we have where both of them are moving, we get an electric field, a magnetic field, and a force. When positive Q is at rest, we have E field, B field, and then the F, again, all in the same directions, all pretty close. We like how they're looking. We just have this extra factor of the V's and gamma. So this is actually a really cool comparison. Now, when negative Q is at rest, we don't have magnetic fields of particles that are at rest or 0, so this makes plenty of sense. And now we're, pretty good. I think this is a great summary and gives us some explicit instruction on how to deal with changing frames of reference, and just a really good problem and exercise overall, I would say. So we'll see you at the next one.